All right, so today we're going to talk about the second law of thermodynamics. And basically, heat transfers are spontaneous, where we go from something that's hot to cold, but never spontaneous in the reverse direction. So it always goes, what I always tell kids is colder items, absorb heat energy. Heat energy tends to give off, and then the items with less energy will absorb that heat energy until you reach a state of equilibrium. So I've got some images here. So in figure A, this is a one-way process. Sometimes you could think of this, and I've actually done research on this, it's called a thermal rectifier. Thermal rectifiers is like a one-way system, right? Oops, I forgot my C. Rectifier. And so basically what happens is it goes from a higher energy state to a lower energy state. So, whoops. I hate when that does that. Okay. And then we'll change the pen color, which is not fun. And then we'll do this. And then we do this. Sometimes I gotta change a pen color. Oh, this is very frustrating. So it always goes from a higher energy state to a lower energy state. So this has got more energy. To a lower energy state with regards to thermal energy, right? Heat energy. And so in figure B, the brakes of a car, when you hit the brakes, the heat dissipates from the brakes and it just kind of gets absorbed by the air around it. Your brakes don't absorb heat from the air molecules. There's friction that takes place here, and then that friction gets cooled by the air. Okay, it doesn't get cooled, it's just that it gets absorbed by the air molecules around it. And then the last figure here, we see that the burst of gas into a vacuum chamber quickly expands to uniformly fill a part of the chamber. The random motions of gas molecules will never return. So that's one way to think about it, right? Like if you let out a little bit of air from like a spray paint can, the air is never going back in, right? Is one way to look at it. There's like a direction that it wants to go, okay? So simply put, the second law of thermodynamics, heat transfers spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. You don't have to do anything for the heat to transfer from a warmer object to a cooler object. You don't do anything. It just does it naturally, spontaneously, all by itself. Okay? But to get heat energy from a colder object to go to a hotter object, it doesn't do that by itself. Okay? And so here's another image for us to consider. Because the second law of dynamics says that I'm going to always kind of flow in this direction. Sometimes we could plop in a heat engine right here. And what the heat engine allows us to do is actually get some work done. Now the work done is the difference between the two heats, right? So I have some heat here, right? That's the hot or warmer temperature. And then at the end, because the work is taking some of that heat energy, right, and converting it, I'm going to have a lower heat here, but it still wants to flow to the lower temperature. Okay, so that's how heat engines actually work, because the heat wants to go from more heat energy to less, and then we can siphon off a little bit of work in the process. Okay, so another way to think of that is that it is impossible for any system for heat transfer from a reservoir to completely convert to work in a cyclical process, which the system returns to its initial state. So in other words, you can't have a perpetual machine because you're going to use up this, right? And so there's no way that I can have it completely come back, because now I'm at a lower, in other words, usually the heat from the higher temperature is going to be greater than the heat from the lower temperature. So I would have to add heat or something that causes heat to keep this as a cyclical process, so it's a cycle. I would have to add some sort of heat or do something that would add heat to the system, is basically what the second law is saying. So how does that work? Well, you could think of it in terms of internal energy, right? So remember that the internal energy of a system is equal to the heat minus the work. Okay? And where Q is the net, so Q is the net heat energy. So think of it like this: Q is equal to the high heat minus the low heat at the end of that system. Okay. And then W is the work done by the system. And so the internal energy, because it's all leaving the system, right? So if you think of this right here, if you think of this being the system, you have heat coming in, work going out, heat going out. So the internal energy should be pretty close to zero. In other words, you should say that the internal energy should be equal to the heat minus the work. And then if you add work to both sides, then the work should equal the heat. Okay? And you could also think of that as being the difference, right? You could, and this is just kind of a side note, it might come up in your homework, the difference in the two heat energies. But that's not the point. The real point is this: your work should equal your net heat. Okay. So this is what is, so the net work done on the system equals the net heat transfer. And so this is for a cyclical system. Process. Okay. The problem is that all processes, there is some heat, QC, that goes to the environment, right? So we're going to lose, some of this goes to the environment, right? And also that whole thing, no energy transfer is 100% efficient. So theoretically, this is kind of hard to achieve, if not impossible, okay? So because of that, we're never going to have 100% efficiency. So in the conversion of energy to work, we always face the problem of getting less out than what we put in. And so we need to keep track of that. So the efficiency, and we'll call this EFF, mathematically will be your work divided by the heat that comes into the system, which is just going to be your high heat. Okay? But also remember that work is equal to QH minus QC. So then our efficiency is technically, oops, oh, I hate when that does that. Let's see if I fixed it. Okay. QH minus QC all over QH, which can be written like this, QH all over QH minus QC over QH. And that could be that our efficiency is equal to, this simplifies to 1 minus QC over QH, the ratio between the hot and cold heat energy. Okay. So making it clear that efficiency of 1 or 100% is possible only if there is no heat transfer. Right? Only if there is no heat transfer. In other words, we're going to subtract this number. Right? We're going to subtract this number here, which means it's always going to be less than 1. And that's the real reason. I'm going to subtract something from 1, which makes it less than 100%. So let's apply this in a practical problem. Okay, so daily work done by a coal-fired power station. That's easy enough to do, right? So you have a coal-fired power station, which is a huge heat engine. It uses heat transfer from burning coal to do work to turn turbines, and those turbines generate electricity. In a single day, a large coal power station, I'm going to try to highlight these, has 2.5 times 10 to the 14 joules of transfer energy from coal, which has 1.48 times 10 to the 14 joules of heat transfer into the environment. A, what is the work done by the power station? And then B, what is the efficiency of the power station? Then the C, it says in the combustion process, the following chemical reaction occurs. Carbon plus O2 becomes CO2. This implies that every 12 kilograms of coal puts 12 kilograms plus 16 kilograms plus 16 kilograms of coal to generate 44 kilograms of carbon dioxide into the atmosphere. And so that's just based on the ratios and the molar masses of carbon and oxygen. And then we're amping it up too. So we're multiplying it by a scalar multiplier. So assuming 1 kilogram of coal is provided, or 1 kilogram of coal can provide 2.5 times 10 to the 6 joules of heat transfer on combustion, how much CO2 is emitted per day by this power plant? Okay, so that's a lot. So let's do one thing at a time. The first thing we're going to do is part A wants to know how much work is done. So remember, work is equal to the hot energy, the hot heat energy, which is not the right way to say it, but that's how I'm going to say it, minus the cold heat energy. So I'm simply going to have 2.5 minus 1.48. Oh, I hate that. And I'm taking a little shortcut. You say, Mr. Adams, why are you taking a shortcut? Because I can. Whatever this is, times 10 to the 14. We could do that because it's the same power of 10, right? So my work is actually 1.02, if you plug that in a calculator, times 10 to the positive 14 joules. Sorry, I crammed that in there. Can I move that down? I think so. There we go. That's a little better. And this is 14. So that's part A. That was pretty easy, right? For part B, what did part B say? We have to find the efficiency of the power station. Well, remember that the efficiency is pretty easy. It's just the work done divided by the hot heat, the higher heat energy. So I would say 1.0. This thing is getting on my nerves today. When I record these, Canva can't keep up. 1.2 times 10 to the 14 joules divided by 2.50 times 10 to the 14 joules. Very annoying. Finally got that fixed. So then my overall efficiency as a percentage, it's really 1.2 divided by this, which equates to about 0.408 or 40.8%. Okay, so that's part B. Not the most efficient, huh? So then part C, this is a little more challenging. For daily coal consumption, I'm told that I've got 2.50 times 10 to the 14th power joules. And then, what was the conversion? 1 kilogram can generate 2.5 times 10. So the way we do this is this is the conversion factor. So it's going to be 2.5 times 10 to the 6. But remember, that's joules per kilogram. And so when you do the math on this, the joules will cancel and it will give you an answer in kilograms. So if you plug that in the calculator, you get about 1 times 10. Well, it's not about, it's exactly 1, right? This divided by this is 1 times 10 to the 8 kilograms. Of CO2, right? That's what we did. Yeah. Hold on a second. So to generate, okay, let me back up. So to generate that kind of heat, if I have this much heat, to generate that kind of heat, this is how much coal I need. So we're not quite done yet. That's the mass, coal mass. That's how much I need to generate the amount of heat that they were talking about, based on the fact that 1 kilogram can generate this much heat. But this is how much heat I have. So what I did is I found that in order to generate this much heat, I have 1 times 10 to the 8 kilograms, right? That's a lot of coal. So then I got to figure out mathematically how much CO2 I have, because that's really the question, okay? So I need to know the mass of CO2. So this is the coal, and then I'm going to calculate how much CO2 is generated, right? So I'm going to take this 1.0 times 10 to the 8th kilograms of coal, because coal is just carbon, right? And then I'm going to multiply that by the ratio of CO2 to coal. So I've got 44 kilograms of CO2, remember that's what they told us, to 12 grams of coal, because that's the ratio of coal to CO2. And remember that coal is just carbon. So this coal cancels with this. I'm left with kilograms. I got to do a bunch of math. So when I'm done with that, I get very frustrating. 3.7 times 10 to the 8 kilograms of CO2. So not that bad. The questions are harder than what you would think. So it's about 370,000 metric tons of CO2. That's not bad. Not too shabby, all right? And that's basically it. Let's move on a little further here. Another type of heat engine is a piston engine. These are like in your cars. Okay. And so fuel comes in, it's ignited, it explodes, right? That explosion causes the gas to expand, but that expansion has heat, right? And the heat and the force, remember that creates pressure times the force is equal to the pressure created in the cross-sectional area, which is the actual cylinder itself, and that forces this down. And then at some point the piston has to come back up and it'll expel the heat plus the byproducts of the actual chemical process, right? Which is the exhaust of the car. So in a 4-stroke internal combustion gasoline engine, the heat transfer into work takes place in a cyclical process shown here. The piston is connected to a rotating crankshaft, which both takes work out and does work on the gas in the cylinder. Air is mixed with the fuel during the air intake in part A, right? B, during the compression stroke, the air-fuel mixture is rapidly compressed, and it's nearly an adiabatic process. But as the piston rises with the valves closed, work done on the gas, right? So here we're doing work on the gas, okay? And that goes to a certain point, and then in figure C, the power stroke has 2 distinct parts. First, the air mixture is ignited, so we ignite it. There's a little spark plug. That's the old school gasoline engines. It ignites it, and that converts the chemical potential energy of the gasoline into thermal energy almost instantaneously, which leads to a tremendous gas increase in pressure, right? Very quickly. And then the piston descends. The gas does work by exerting force through a distance, right? So that's it's a near adiabatic process. And then part D, the exhaust stroke expels the hot gas to prepare the engine for the cycle again. So this is one full cycle of a gasoline engine. One way to look at that is like this. So remember when we talked about adiabatic processes a couple of sections ago, or maybe it was the last section ago, you know, the cycle repeats itself. You go from A to B to C to D, right? So that's what we're referring to. On the right, we have this internal energy. So you have heat coming in, work being done, heat going out. This is very similar to a piston on a car, right? So this is known as the Otto cycle. So a lot of our heat engines are based on an Otto cycle. That's what this is, okay? So then an Otto cycle produces a greater work output than the one in figure 18, because the starting temperature of the path CD is higher than the starting temperature in AB, which is lower. The area inside the loop is greater, corresponding to the network output, right? So the volume, so we got to track this, right? It's pressure versus volume. So here, the pressure is higher, right? That we have heat coming in, and then as it comes out, we have heat going out. And so then what happens to the volume? Well, the volume decreases when the volume increases. As the volume increases, what we have is a decrease in pressure, right? Then that pressure lessens even more, and then the process starts over where we go back and we have a decrease in volume, which causes an increase in pressure. When we add the heat, we have the pressure increases, then we release it, and then it goes back and forth. So this whole thing is considered the Otto cycle. We have the internal energy that creates this heat here. The heat goes into a system, right? Work comes out. The remaining heat energy comes out, and so the W proportional to the shaded area of the PV dot, the pressure volume diagram. Okay, so that's basically it. And so you'll have some questions where we'll talk about this process. But the Otto cycle is like, it's how most heat engines work to some degree. The only thing that really varies is what is the work that's done and how is the work done. Sometimes it's used for generating power plants. Sometimes it's used for, cars going back and forth. But this is like a basic steam engine type thing. But the pistons and the turbines and all that stuff, basically you have heat coming into a system. Then there's some work done by that heat energy somehow, some way. And then there's still a lot of heat in the system, so the remaining heat gets left. And so the work is really the difference in the high heat minus the cool heat. It's just the net heat energy when you think about it. Okay, that's it.